Welcome my friends, welcome to my next lecture. Now this lecture my plan is to talk about what is called statement of Green's theorem, and I will of course discuss a proof of it, and then I will talk about one example using Green's theorem. One example I will talk about. So that's my plan. So in my last lecture I talked about like the notions of contour. Of course I have discussed those concepts long before. Just to recall those concepts I have again discussed in my last lecture. Now this lecture I will start with the notions of what is called simply connected domain, because I need it for the statement of Green's theorem. So I will start with simply connected domain, and then we will have a multiply connected domain, and then I will start with what is the statement of Green's theorem, and then one example I will talk about. So that's for today's plan. Okay, so as I said, so I should start with, or I should recall with the notions of what is called simply connected region. So what is simply connected region or simply connected domain? So this is the definitions I have written. So this is simply connected. Of course last couple of lectures before I have discussed this kind of, in fact I think at the very beginning I have discussed. Anyway, recall those notions once again. So the definition is the following. So a connected set is said to be simply connected if every simple closed smooth curve or piecewise closed smooth curve lying inside S and which encloses only points of S. So that means there should not be the case, that means I have a simple closed smooth curve or piecewise smooth curve in my what is called connected set S, and there are interior in the region bounded by this simple closed curve, there should not be any point which is not in S. So that means, in other words, every simple closed or piecewise simple closed smooth or piecewise smooth curve C which is lying inside S which encloses only points of S. So that means there should not be any point which is outside S. Okay. So this is called simply connected domain. A connected set which is not simply connected, it's called multiply connected set. Now look, I have drawn two pictures. It will be more clear that what is the kind of this example. That one, this is simply connected. Why? Because what is the definition? If I take any simple closed smooth curve C lying inside S, it should contains or S, that curve lying inside S encloses only point of S. So now look, if I take this kind of curve, right? A simple closed curve, right, smooth curve. So now look at the portions which encloses my curve. So that means this is the portion, and this is actually is in the sets. This is the light blue. Okay. So therefore whatever small closed contour or simple closed smooth curve you can take, so it encloses only points in S. In other words, you can say that there should not be any hole. If there is a hole, and if I take a simple closed smooth contour around that point, that means it is not the case that it encloses all the points of S, because there is a hole, because there is a point which is not in that S. So therefore this is very nice, simply connected. Now look, this region what I drawn is that not simply connected. Why? Because if I take this simple closed contour, of course it encloses all the points of S. That's perfectly all right. But what is the definitions? It says that a connected set is said to be simply connected if every simple closed piecewise smooth curve lying inside S and it should encloses only points of S. Now you see, if I take this kind of smooth curve, this is a simple closed smooth curve, this is my C, okay, lying inside my S. Now you see what is the region encloses the curve C. So this is the region, it's okay. At the same time this portion is also there, na. Now this portion is not an element of the collection S, because there is a hole, this is a hole, this is a hole. So therefore this portion is actually outside the set. So therefore even if I have a simple closed smooth curve sitting inside my what is called connected set S, but it encloses not only the points of S, it encloses some points which is not in S. That means these are the portions which encloses, but it is not a part of my connected set S. So therefore it is not simply connected. So therefore simply connected means there should not be any hole, and if it is not simply connected, that means if it is multiply connected, I mean there should be a couple of holes will be there. So this is called simply connected and this is called not simply connected. Okay. So I think the definition is clear. Once I have the notions of simply connected and multiply connected set or region domain, then now I am talking about definition of domain. What is said is that an open and connected set in R2, again I am in two-dimensional Euclidean space. So an open and connected set in R2 is called a domain in R2. So if I next time if I say that suppose let's D be a domain, that means I actually am talking about the set D which is a domain, that means it is open as well as it is connected set in R2. Okay. So a domain together with some, none or all of its boundary points is called a region. Okay, that's my definitions. So that means if I start with that, okay, let D be a domain in R2. So what does it mean? That means I say that, okay, that set D is open as well as it is connected. Now if I say that D is a region, region means of course domain is a region. Now look at the definition, a domain together with some, none and all of its. So that means if I have a domain which is open connected and no boundary point, so that means it is again a region. If I start with domain D which is open connected along with some boundary points, it is also a region. And if I start with my domain which is open connected along with all boundary points, that is also a region. So therefore start with a domain which is open and connected, and if I say that take your domain D and take the union either some of its boundary points or all of its boundary points, or suppose no boundary points, then this is called a region. Okay. So that is my definition. One results I have said is that if D is a simply connected domain in R2, that means D is a domain in R2, that means it is open and connected and it is simply connected at the same time. So it is simply connected domain, that means it is domain as well as it is simply connected. So therefore if D is a simply connected domain in R2, then the boundary which I denote it as del of D is a simple closed curve. So therefore if I start with a D which is simply connected domain in R2, and then if I just look at the boundary of this domain, it becomes a simple closed curve. Further, if I just take the union of my domain D along with all the boundary points, that means union of del D, then the new set which I denote it as D closure, that means the set along with all boundary points, it is also simply connected. So therefore if I start with a simply connected domain in R2, first observation is that the boundary of my domain D which is a simple closed curve, and if I make a new set, that means my domain along with all the boundary points which I denote it as D closure, I am saying this is also a simply connected. For example, I draw a picture, look at this. This is a domain. So here boundary point dot 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 means it is not included, that means the open set I am talking about. So this is a domain, right? It is open, it is simply connected, it is connected, simply connected means connected, so therefore it is very nice. So this is a domain, simply connected domain in R2. Now what is the boundary? Boundary is nothing but this circle. This red one, this is a circle, this is nothing but del of D which is a simple closed curve. And if I talk about the set D along with all the boundary points, that means it is this along with this boundary, that means the points on the circle, it becomes also simply connected because this is denoted as the closure of D. Okay. So therefore this is a domain D which is simply connected domain in R2. If I just take the union of all the boundary points, it is also simply connected. And of course the boundary of your simply connected domain is a simple closed curve because it is straightforward from the pictures. That is one result. What is another result? Another result says that if I start with a simple closed curve in R2, suppose I am in R2, start with a simple closed curve, suppose this is my C in R2, then the interior bounded domain D enclosed by C, that means, so this is the interior domain that I denote it as D enclosed by D. The interior bounded domain D enclosed by C is a simply connected domain. So therefore you can look this from the picture, this is also simply connected domain. So therefore that means I have two kind of observation. One is that if I start with a simply connected domain, then its boundary del of D is a simple closed curve. That's how I have written. That is the first result. Second result is that if I start with a simple closed curve and if I look at the region encloses or interior region bounded or enclosed by my simple closed curve C, if I denote it as D, this is also a simply connected domain. So this is an if and vice versa, if and only. That means given a simply connected domain, the boundary will be a simple closed curve. Given a simple closed curve in R2, the interior bounded domain enclosed by your simple closed curve C, which I denote it as D, it is also simply connected. So this is if and only. Okay. So that means if I suppose say look at, give me one example of a simple closed curve. You just say that okay, start with a simply connected domain and look at the boundary del D. It is a simple closed curve. Or if I say that okay, give me an example of a what is called simply connected domain in R2. What you do? You start with a simple closed curve in R2, look at the interior bounded domain enclosed by your simple closed curve C, which is a simply connected domain. Okay. So I think it's clear. For example, I draw a picture. Look, so this is my simple closed curve C. So suppose in these directions. So this is the region enclosed by D, which is actually simply connected. And if I start with a simply connected domain D here, then boundary is a simple closed curve. So therefore it is a vice versa. That means simply connected domain in R2 go to the boundary, it becomes a simple closed curve. If I start with a simple closed curve, if I look at the interior bounded domain encloses by simply closed curve, it becomes simply connected domain. Okay. Again I am recall ideas needed for the Green's theorem. Again, if I just combine whatever I have discussed till now. So, this is the example of a simple closed curve, but this is not simple because there is a 8 figure or there is a cross here, injectivity losses. So, that which is not simple. So, this is positively oriented or anti-clockwise or counterclockwise direction. This is positively oriented and this is negatively oriented. That means this is the clockwise opposite to this one. This is a simply connected domain and this is not simply connected. I mean, this is a multiply connected. Simply connected means there is no hole, and in the multiply connected or not simply connected there are a couple of holes are there. Okay. I need some notations to talk about the statement of Green's theorem. What is that? It says that the vector. So, now you see, I think few lectures before I talked about two concepts. One is vector line integral for scalar valued functions, and I have a vector line integral. Okay, I should say like scalar line integral or vector line integral. So, that means when I talked about scalar line integral, that means I gave the notions, I discussed the notions of line integral for scalar valued functions, and later I talked about the notions of line integral for vector valued functions. So, therefore, vector line integral, that notions I have already discussed. So, what is the notations here? So, the vector line integral, you will see that notions of vector line integral involved in the statement of Green's theorem. That is what. So, therefore, recall the notions of vector line integral. So, the vector line integral over a closed curve. Suppose if I have a closed curve, so the vector line integral over a closed curve I will denote in this notation. This is the integrations. Now, look, if I have a circle there, so that means I am talking about the vector line integral over a closed curve, and the vector line integral over a closed oriented counterclockwise curve. If I have, therefore what? Therefore, I have a notions of vector line integral. That means I have to integrate a vector valued functions over some curve, and if that curve is closed curve, then this is the corresponding vector line integral notations. And if I start with a closed curve which is oriented either clockwise or anti-clockwise, so that means this is the corresponding notation. So, this notation you see, if I put a arrow here, that means it is actually, that means I am talking about the vector line integral over a closed curve which is oriented positively or which is oriented counterclockwise or which is oriented in the anti-clockwise directions. And if I talk about vector line integral over a closed curve which is oriented say negatively or clockwise, so this is the corresponding notation. So, looking at the arrows, you can at least guess which vector line integral, what vector line integral I am going to talk about in which closed curve, whether it is positively oriented or negatively oriented. Of course, if the arrows, and if I only there is a only circle is there, that means I am actually giving a meaning. I want to talk about the vector line integral over a closed curve. Okay. So, this is the notation. So, vector line integral over a closed curve, this is the corresponding notation. You have an integration, again the closed circle will be there. And if I want to talk about vector line integral over an oriented closed curve, whether it is clockwise or anti-clockwise, depends on the notation, you will see. Okay. So, these are the, of course, again when I talked about the notions of vector line integral or scalar line integral, particularly vector line integral, that kind of notations I already discussed, if you remember. Okay. Okay, so now I think I am in a platform to talk about the statements of Green's theorem, because whatever concept I have discussed like contour, closed contour, simple closed contour, Jordan curve, and then there is orientations, and then I just talked what is simply connected region or multiply connected, and then I talked about domain and region. So, almost all concepts are needed, those concepts are needed to talk about the statements of Green's theorem. So, first that is what I have written. So, Green's theorem for simply connected region. So, I will start with a region which is simply connected, and there I will make a statement of Green's theorem. Okay, let us see what is the statement. Okay. So, that is what I have written. So, this is Green's theorem for simply connected region. That means you start with a region which is simply connected. Okay. What is that? Okay, very nice. Look, so that is the theorem. This is called Green's theorem. I am just in bracket I have written it is the tangential or curl or circulations form. Okay. So, this is a statement for Green's theorem over a simply connected region or domain, and which is of the form tangential. That means you will see that when I talked about vector line integral, there is a tangential component of your vector field, if you remember. So, in fact, when I just finish the statement, then you will see why the term tangential or curl or circulation form is there. That will be reflected in the statement. Okay. So, okay, what is the statement? It says that, so let capital F, which is capital MXY I cap plus capital N x y j cap. Suppose it is a continuously differentiable vector field on an open set S in R2. So continuously differentiable vector field means what? So that means the components are m comma n. This is continuously differentiable means what? This is differentiable. That means partial derivative of m and partial derivative of n both are exist and continuous, and continuously differentiable, that means derivative exists at the same time, derivative is also continuous. That means I am starting with a very nice vector field. Okay. So that means I am starting with a continuously differentiable vector field. That means that vector field is differentiable, at the same time derivative is also continuous. That means a very nice vector field on an open set S in R2, sitting inside R2. Let C be a positively oriented piecewise or smooth simple closed curve in S. So I have a domain a open set S in R2. Consider a curve C which is positively oriented, smooth, simple closed curve sitting inside S, such that the interior bounded domain D enclosed by my curve C lies entirely inside S. Now look at this picture. This picture I have drawn, it's clear from this picture. So this is my open set S. So this is my open set. Okay. Then what I have done, so let C be a positive. So look at the curve. This is my curve C. C is positively oriented because arrow is given in the anticlockwise directions. It is smooth. Looking at the picture, it is clear. It is simple and it is also closed. Okay. So everything is there. So C is a positively oriented, smooth, simple closed curve in S, such that the interior region. So interior region means that I have denoted as the yellow color. That is the D, which is lies of course entirely in S. Now what you do, set the region R, which is nothing but the region bounded or encloses by my simple closed smooth curve inside S, which is D, along with the what is called the boundary of my domain D. So that I denoted as C. That means along with the curve C. Now of course if I take the union D along with the boundary of D, which is nothing but C, that is also of course that R is also contained in S, and as I just said, if I have a curve C which is say smooth closed curve C in S, then the region encloses or interior bounded domain encloses by your curve C, and if I take the union of my boundary one, then it becomes a simply connected, right? Of course the interior one is simply connected, and if I take the all the interior domain along with all the boundary point, that is also simply connected. So that is why R is also simply connected, that I have already discussed. If you remember, if you go back, so you see, so D is a simply connected domain, the boundary is a simply closed curve, and if I take the closure, that means the domain along with the boundary, that is also simply connected. Okay. So that is the point I wanted to make. So therefore R is this domain D which is simply connected domain open, and if I take the boundary one, that is also simply connected. Okay. Then what is the statement says? Statement says that the vector line integral, if you remember the notion, this is the notations of vector line integral. So capital F is a vector field, C is a positively oriented smooth simple closed curve in my open set S. Then this is the notations of vector line integral, integration C F dr, which is nothing but the scalar line integral. That means what you have to do, you have to take the dot product with your vector field F and the what is T? T is the tangent at that point actually, if you remember. Okay. If you remember that one, what is T? Suppose your curve is C and suppose C has a parameterization R. Suppose this is, I have a parameterization R T, T say running over from A to B. Then what is my tangent at the point R T in my curve? So this is nothing but, now suppose curve is smooth, that means R derivative of R at the point T is non-zero. So therefore if you remember, this is nothing but I think R prime T divided by norm of R prime T. So that is the tangent vector. That means if I have a curve, so that means if I take a point, so this is the corresponding tangent, some directions it follows. So that means if my curve is smooth at each point RT in my curve, then the tangent R prime of T is non-zero. So that is the definition of smooth curve. So therefore I can talk about the notions of what is called unit tangent vector T, and then what you have to do, so that means a vector line integral of capital F over my simple closed curve C, which is nothing but the tangential component of my vector field. That means you just take the dot product of F with T and calculate the what is called scalar line integral of these functions. Okay. So therefore this vector line integral of capital F over C, which is same as the scalar line integral of the tangential component of my vector field F, which is nothing but F dot T over C, which is same as, it is the double integral over the region R del n del x minus del n del y, and which I can write it as integrations of double integral over R curl of f dot k cap, because I can see my f inside R3 also, right, because this capital F, which is m times I cap plus n times j cap plus 0 times k cap, because I can look at my vector field sitting inside R3, right, and then you just calculate the curl of this vector field dot with the what is called vector k cap, and this turns out that it is becomes like this one, del n del x minus del m del y. Okay. So, this is the statement. So, that means what it says is the following. It says that if I start with a continuously differentiable vector field on an open set S, and if I consider a simple closed positively oriented smooth curve inside C, and if I look at the region bounded by simple closed curve C, which I denoted as say D, which is also simple closed, just now I have explained. And if I look at the region R, which is nothing but the region, interior region bounded by simple closed curve along with the curve itself, which I denoted as R, then I am saying that you just look at the vector line integral of your vector field capital F over C, which is exactly equal to the double integral over the region R of this quantity. In fact, you can see this integral actually the same as integration over D, same del n del x minus del m del y. That means it says that doesn't matter whether I am including my boundary of D or not. So, even if I include my boundary of D, which is nothing but C, so this double integral over R, which is same as this double integral over D, because if you remember the double integral I have defined in terms of Riemann integral, okay, and Riemann integral over this set D or the set R, which is nothing but D union the boundary, which is the curve, both are same. So, whether I can write it double integral over R or double integral over D, both are same. But it is very important, it is very nice. Now, if you see the like for example, if I talk about the fundamental theorem of integral calculus, what is that? So, what is that? Suppose if my function is very nice, the statement says that integration a to b derivative of x dx, which is nothing but fb minus fa. Correct, if you remember. So, suppose my function is very nice, that means it is differentiable, continuity, all properties of my function has. Then if I evaluate or if I integrate my derivative of f over the interval a to b, which value is nothing but the value of f at b minus value of f at a. Now, you see this is my interval a to b, right. So, therefore, I can say that this integrand, the left hand side, that means derivative of f prime over the full interval a to b. So, in the right hand side I can evaluate that integral, the evaluation of my function f at the boundary point, right. So, that means somehow I reduce my integral, one dimensional integral, this is one dimension, na? This one dimensional integral to the 0th dimension. That means the right hand side is actually the evaluations of f at some point. So, that means one dimensional integration I can reduce to the one dimension more, that means 1 minus 1, that means 0 dimension. So, that is the fundamental theorem. Now, you can interpret in this way also. So, Green's theorem also I can think about, see look, I have a region, I have a simple closed curve C, I have a region either D or R. So, what I am saying is that the integration over the boundary, that means the over curve, which is same as integration over the region. So, I can think about that. So, look at the region D, which is a 2-dimensional region. So, therefore, I can reduce the double integral to a what is called 1 dimension less, that means to a line integral. So, that is how you can also think, like in the fundamental theorem. I have a integration over say interval that I can reduce to a what is called integral over a discrete set or 0th dimension. That means integrations over f prime, which is nothing but fb minus fa. So, now I can interpret in this way also. I have a double integral, that means I have a integration over the region in R2 that I can reduce to 1 dimension less. That means I can transfer that double integral over the region R to a what is called line integral, that means 1 dimension less. That means this the left hand side is the integral over this curve, this is 1 dimension. So, that is why you can also think about like Green's theorem, you can think about like fundamental theorem in the what is called single variable calculus. Like fundamental theorem, if I have an interval AB, so if I integrate my f prime, that means I am just 1 dimension, that means I have a length, I have an interval AB, which is I can think about as a 1 dimensional integral, then it is exactly equal to fb minus fa. That means the right hand side becomes 0th dimension, that means evaluations of my functions at a point. Same way I can interpret my Green's theorem, I have a double integral over the region R, which is subset of R2, that I can reduce to 1 dimension less. That means that is exactly equal to the integrations over some curve which is 1 dimensions of my functions capital A. That is why you can also think about that. Okay. So, therefore, I think it is clear what is the statement of Green's theorem. So, start with a continuously differentiable vector field. on your open set S in R2, start with a simple, closed, smooth, positively oriented curve in S. Look at the interior bounded domain D enclosed by C, which is like entirely in S. Consider the region R, which is the region D along with its boundary, which is nothing but C. Then R is also simply connected, I already said. Then it says that the corresponding vector line integral of my vector field capital F over C, which is nothing but the scalar line integral or tangential component of F. This is the scalar valued functions. The scalar line integral of F dot product with T over my curve C, which is nothing but the corresponding double integral over the region R, and this time integrand will be del n del x minus del m del y, which is where m and n are the corresponding component of my vector field, and which I can write if I look at my if I interpret my vector field in 3-dimensional. This is nothing but curl of F dot k cap. So what is curl of F? So what is my, if I look at my vector field inside R3, so what is the component? This should be capital M, capital N and 0, right? And then what is the curl? So if I calculate it, this is nothing but I cap, j cap, k cap. Okay, so curl means what? So curl of F, if you remember, this is gradient cross F, right? So gradient means what? I have a del del x, I have a del del y, I have a del del z, right? That will be there, I j cap, and then you have this vector field. That means I have m, I have a n, I have a 0, right? So this is called, this is actually give you the curl of F, right? Now what if you just calculate it, you will what is, if you just calculate it, the vector you will get. Okay, let me just calculate it. So do here. So therefore first one is I cap times, so this is 0, so that means this should be, again this will be 0 because m n, n is a function of, so this is, I should write x comma y, this is x comma y. So therefore this is 0, this is, so I, there will no contribution in I cap, minus j cap. Okay, so what is this? This is 0, again this will be 0 because it is a function of x and y variable, this is a function of x y variable, so only k cap will survive. What is k cap? K cap is this one, that means it should be del n del x minus del m del y. So this is the vector. So what is my vector? I will have a vector 0 comma 0 comma del n del x minus del m del y. That's my curl of F. And what is my k cap? Again 0 0 1 is k cap, and if I take the dot product, what will given? It is exactly equal to del n del x minus del m del y, that double integral. Okay. So now I think it's clear that what is the statement of Green's theorem. So start with a nice vector field, that means continuously differentiable vector field over an open set S. Your variable x and y varies over open set S in R2. Take a simple positively oriented closed smooth curve inside S and look at the region D, which is interior bounded domain encloses by your curve C. Okay. Look at the region R, which I am saying that consider the domain D along with its boundary, which is nothing but C. That is also simply connected. Then it says that the corresponding vector line integral of capital F over C, which is same as the scalar line integral of F dot T, which is nothing but the tangential component of F, which is same as the double integral, whose integrand is del n del x minus del m del y, which I can write if I look at my vector field inside R3, same as curl of F dot k cap times over R. So this picture is clear. So therefore also I said that you can think about that I can reduce my integration one dimension less, like in the fundamental theorem of integral calculus in the real variable, you know, in the single variable case. That means I have a double integral over some region R, then it is same as like integration over one dimension less, that means over a simple closed curve. Okay, see. So that's what, that's you can interpret in this way as well. Okay, so what is the proof? So proof says that, proof is very nice. So what I will do, I say that okay, first we assume that my region is both vertically and horizontally simple. Now if you remember, I talked about that notions of vertically simple and horizontally simple again when I talked about double integral, if you remember. So what is vertically simple? Vertically simple means, so I have a region in R2, that means I have two variables. So x should varies from fixed a to b, whereas y should varies from function of x to function of x. So that's the kind of vertically simple. If you remember the picture, so this is my AB or x runs over, but however y should run from some curve to some curve. So suppose this is a function of g1x and this is a function of g2x. So y should varies from g1x to g2x. So this is the kind of simply connected domain. This is called what is called vertically simple. And what about horizontally simple? Same thing. This time y will vary from one number to another number. So that means you will have y fixes from say C to D. However, x varies from some curve to some curve. So then this is, maybe you can write g1 of y, and this is say g2 of y. So therefore x varies from there to there. This is called actually x varies from some fixed number a to b. This is called, and y varies from some function of x to some. So I can write it a less or equal to x less or equal to b, and g1 of x less or equal to y less or equal to g2 of x. So this kind of domain, it's called, what is called your vertically simple. And what about this kind of domain? So this kind of domain, it's called what is called horizontally simple. That means here y varies from C to D, and x varies from g1 y x less or equal to g2 y. So horizontally simple and vertically simple I know, but I am starting with a region R which is both vertically and horizontally simple, like this one. Okay. If you remember, when I talked about the given example of a region which is both vertically simple and horizontally simple, this is the region you can have it. Okay. So it says that first assume that the region R is both vertically and horizontally simple. Otherwise, if it is not the case, then we can break up into compositions of such regions. That means even if I given a complicated regions, I can break my regions into finitely many, what is called region which is both vertically simple and horizontally simple. And let's see whether the proof works for the vertically simple in a region which is both vertically simple and horizontally simple. If I prove that one, and if any region, if I break up into finitely many pieces, on each pieces is both vertically and horizontally simple, then I am done. Okay. So that's exactly. So therefore, suppose assume that your region is both vertically simple and horizontally simple. Suppose this is the region you have. Okay. So then, like if I draw a picture, you can have it. So this is both. So suppose, so this is x axis. So suppose this is my y is equal to a, and suppose this is my y is equal to b. Okay. So what I will do? So I will start from. So what I will do? So I will start from. So maybe I should put a arrow. So suppose this is my point. Okay. So I am starting from here. I am going in these directions, in this direction. Then I will come back in these directions. Okay. So that means I can think about this is as a horizontally simple. Okay. It's y running from a to b in the, but x running from g1 y to g2 y. So that means I can think about as a what is called horizontally simple region and perform my calculations. Okay. So first observation is that we will show that this integral over line integral over c n dy, which is same as the corresponding double integral of the partial derivative of n with respect to x variable over r. What is that? How to calculate it? Look. So LHS. So that means integral, this line integral of the integrand is n dy, which is this c. What is my c? C is my c1 union c2. This is the region C. C is the simple closed curve which is C1 union C2. That means if I start from here, I am actually moving in this direction. So anti-clockwise or counter-clockwise direction, that means I am talking about the positive directions. So therefore your C is equal to C1 union C2. What is C1? C1 is this portion starting from here, this is the G1 of y, and what is C2? Starting from y, ending here, so this is the G2y. So C1 is G1 of y, C2 is G2 of y. And what is your C, which is the C1 union C2. So now let's see, calculate the left hand side. Left hand side is the line integral of n over c. Now I can break up my simple closed curve c into two parts. One is integration c1 plus integration c2, because these are disjoint. So I already said that properties of line integral, scalar or vector line integral. So because if I have two contour c1 and c2, and suppose they join in such a way so that the end point of c1 is the beginning of c2, so then you can do that. So same thing is going on. So this is my c1, so end of c1 which is the beginning of c2, so not an issue. So therefore this perfectly all right from the properties of line integral. Then what you will do, now look at, so now c1, which I know what is my c1, this is the curve g1 of y, that means I have the parameterizations corresponding, this is g1 of y I know. So therefore if I want to just make it to a y variable, then what will happen? I have the integrand capital N, so I have a capital N x comma y. Now this time c1 is particularly given where x is equal to what? X is equal to g1 of y, right? So now look, here y is a and y is b. So therefore c1, that means I should start from here and I will come back here. That means I am starting from y is equal to b and then ending y is equal to a, and at the time x is actually taking the value g1 of y, because my c1 is nothing but x is equal to g1 of y, right? That you can think about as a parameterizations of your curve c1. Okay. So therefore this integral turns out y from b to a, capital N, you just replace x by g1 of y, comma y dy. That's perfectly all right. Okay. And what about C2? C2 is the curve x is equal to g2y, that is the corresponding parameterization of C2. So now this time I am moving in this direction. Now I am starting from here, moving in this direction. So therefore it starts from A to B, that's you see y from A to B, and then you have n x comma y. But what is your x? X is equal to g2 of y, because this is the corresponding parameterization of C2. So therefore n of g2y comma y dy. So therefore this is the corresponding the line integral over the simple closed curve C of my functions n. Okay. Now if I combine this one, because it is the rule of line integral, so it is b to a, that means I can flip it from a to b because it is a Riemann integration. So okay, so that means only minus 1 will come out. Again it's from y from a to b, n of g1 comma g1y comma y dy, plus y from a to b, n of g2y comma y dy. So therefore left hand side the corresponding line integral of capital N, it turns out that minus of this plus this one. Now you just calculate the right hand side. So right hand side, what is that? Now if I calculate the right hand side, which is nothing but the integral over r, or this is same as you can think about integral over d, both are same, okay, of nx dA. Okay. But what is the region? This is the region encloses by simple closed curve C. This is the region R. Of course, if I talk about R, it encloses the boundary as well. But if I want to talk about D, that means it is nothing but the interior bounded, open bounded domain, right? So that means D. So what is that integral? So therefore now you know when I talked about double integral, and if I have a region like that, then you can write it in terms of what is called iterated integral. So therefore you know this region is what? Horizontally simple region. In fact, both vertically and horizontally simple. I am actually for calculation purpose I am thinking it is as actually horizontally simple region, and you know that integrations over horizontally simple region, how to using Fubini's theorem I can write in terms of what is called iterated integral, because I am looking at it as a horizontally simple, that means y running from here, y running, so y running from a to b, so that means a less or equal to y less or equal to b, and x is running from what, g1y to g2y. So therefore g1y less or equal to x less or equal to g2y. Right. So if I want to calculate the double integral over this region, so I can by Fubini's theorem I can write in terms of what is called iterated integral. So therefore since the region is horizontally simple, I have to first integrate with respect to x variable, right? So that means that's exactly I have done. You see, I have to integrate first x variable and then I have to perform the integration with respect to y variable. And since the region is what is called horizontally simple, so therefore this double integral is nothing but, so integrand is nx del n del x at the point x comma y. So means I have to first integrate with respect to x variable, because x running from g1y to g2y, so that's x from g1y to g2y. Then whatever I will get, it's a function of y, and then you have to integrate with respect to y variable, and y varies from a to b. So this kind of things I have already discussed when I talked about what is called double integral. Okay. So therefore right hand side this double integral, whether I am talking about over r or d, it exactly equal to this iterated integral. Now you can calculate it. What is this? See, so keep y from a to b as it is. Look at this integral. What is this? This is nothing but del n del x at the point x comma y, and I am integrating with respect to x. What is that integral? If I think about y is fixed, so think about this integral as a function of x. Now you use the fundamental theorem of integral calculus for fixed y. So this is nothing but integration from x from g1y to g2y, and by fundamental theorem what is this? This is nothing but the value of n at the point x, x means g2y comma y, minus value of n at the point g1y comma y, isn't it? Because it is a fundamental theorem. Keeping y variable fixed, think about is a function, think about the integrations over x variable, and what is the integrand? It is derivative of capital N. So therefore by fundamental theorem of integral calculus, this is nothing but the value of n at the point, what is the upper limit, g2y, so g2y comma y, so this is g2, I should write. So n of g2y comma y minus n of g1y comma y. So therefore the right hand side this double integral, whether it is over r over d, which is nothing but integration from y from a to b in capital N of g2y comma y minus capital N of g1y comma y. Okay. So now I have the left hand side, I have the right hand side. Right hand side is this one. What is the left hand side? If I combine these two together, again integration y from a to b, n of g2y comma y minus n of g1y comma y. So therefore left hand side is equal to right hand side. So therefore since the expression of left hand side and right hand side are equal, so therefore the corresponding line integral of capital N dy, which is same as this double integral of del n del x over the region R or D, whatever it is, it's up to you. Whether I am talking about R or D, both are same. Okay. So therefore the one part, that means the line integral of capital N which is a function of xy over the simple closed contour C, which is nothing but the double integral over the region R or D of the partial derivative del n del x. Okay. Same way, exactly same way, if I do the same process, if I calculate the left hand side line integral, which turns out that this is exactly equal to the double integral over del m del y over the region R or D, but this time we will have one minus sign we will have. Okay. You just calculate it in your home, it will be clear the way I have done it, because left hand side again you just break up into two parts, C1 and C2, just do the things. Okay. So you have a C1 and you have C2, C1, C2 parameterizations you know, so you can have the left hand side calculation very easily. Right hand side also you can do that, because you have the region, and the region is what is called horizontally simple and both vertically simple. You just use that how to calculate what is called double integral over horizontally region or vertically simple region. By Fubini's theorem you can write it in iterated integral, and you can conclude that this line integral of capital M over C, which is nothing but minus 1 times the double integral of del m del y over the region R. Then what you have to do? You have to just add it. So therefore integral, vector line integral of capital F over C. If you remember when I talked about vector line integral, and if my vector field has a component m comma n, then this vector line integral, which is nothing but the corresponding what is called line integral of m dx plus n dy over this what is called closed contour C. Now this is same as integration C m dx plus integration C m dy, and of course integration C n dy and integration over C m dx I calculated. If I combine together, this is nothing but the double integral over the region R of this integrand. That means this is del n del x at the point x comma y minus del m del y at the point x comma y times dA. So, okay. So, I think that is the proof of it. So, okay. So, it is very easy proof, very kind of nice way. When I, of course, I started with very nice region, I should say. So, I am started with a region which is both vertically simple and horizontally simple. If I have that region, then the proof is that just you have to see that in that region how to calculate your double integral and how to calculate the corresponding what is called line integral. If I do that, just look at the left hand side and right hand side, if the both value are same, and you can do that. So, again I just repeat once again. So, again, so start with a very nice region which is both vertically and horizontally. If it is not that nice your region, then I can break up into this nice region. So, therefore, it is enough to prove the Green's theorem on the nice region which is both vertically and horizontally simple. So, I am starting with this kind of domain. I am thinking about it is horizontally simple. So, that means y runs from A to B, x runs from G1y to G2y. So, G1y is the parameterizations of my curve C1, G2y is the parameterizations of my curve C2. Then what I am doing first, I am calculating the line integral of capital N over the simple closed contour, smooth contour C, and I show that this is exactly equal to the double integral of my del n del x over the region R. R is nothing but the region bounded by your simple closed curve along with the boundary. Of course, you can also think about this is same as integration over D, that does not matter, both are same. Okay. So, you should not worry about that. So, what I do first, I have calculated the left hand side. C can be break up into two parts, C1 and C2. Then I just use the parameterizations, and if I do the integration, so it turns out that this is nothing but y from A to B, n of G2y minus n of G1y comma y dy. That is the left hand side. What about the right hand side? Right hand side, the double integral over R or over D. Since the region is horizontally simple, I know by Fubini's theorem what will be the corresponding what is called iterated integral. So, since y varies from fixed number A to B and x varies from some function of y to some function of y, so therefore, first you have to perform the x integral and then y integral. When I perform the x integral, keeping y variable fixed, so use the fundamental theorem, you will have n G2y, capital N of G2y comma y minus n capital N of G1y comma y, and then you have to perform the y integral from A to B, and then I see both LHS and RHS are same. So, therefore, I have line integral of capital N over C, which is double integral over double integral of del n del x over the region R or over the region D. Same way you can prove that the line integral of your capital M over simple closed contour with respect to x variable, which is same as the double integral of del m del y over the region R or over the region D, but there should be a minus signs. Now, you just add it. So, therefore, your vector line integral of capital F dr, which is same as this is the corresponding line integral m dx plus n dy. If I combine it together, it gives you the double integral over the region R or over the region D, does not matter, both are same, del n del x minus del m del y dy. So, this is the corresponding proof of your what is called Green's theorem. I think I should stop here. So, therefore, I have discussed my simple connected domain or simple connected region, and then I talked about the statement of Green's theorem and I give the proof. So, again there are many proofs, but this is one of the proof I have given. Of course, I am starting with my domain is nice. I can break up into what is called very nice region, which is both vertically and simple. Okay. So, I have discussed my Green's theorem statement. I hope it is clear. Somehow you can interpret like fundamental theorem, like you can reduce your dimension of the integration. That means you are starting with a double integral, you can reduce to one dimension less. That means in the what is called line integral. Like the fundamental theorem in the single variable, you have a integration over one dimension and it becomes reduced to the 0 dimension. Here I am having integrations over what 2 dimension. I am reducing to one dimension less. So you can think about in that way as well. Okay. So therefore, so today I have discussed mainly the statement of Green's theorem and proof. In my next lecture, I will just see the applications of my Green's theorem. That means I will calculate couple of examples, then it will be more clear that how Green's theorem one can apply to solve some problems. Okay. So that's my next plan, and in fact I will start with those discussion in my next lecture. I think I should stop here. Thank you.